Dr. Hagelstein. He will talk something. Yeah, go ahead.
Thank you, Professor Kasagi, and thank you for the organizers of the conference to having put on a fantastic conference, which I'm enjoying tremendously. I want to talk about statistical mechanics models for palladium hydride, palladium deuteride phase diagrams. Palladium hydride is very important historically. It's perhaps the best studied of all the metal hydrides. A lot's known. The first modeling was done for it. There's mean field models in the literature. Phase diagrams are available. Historically, once the partition function or entropy for the ideal gas was figured out, that allowed you to match the chemical potential for the ideal gas with the chemical potential of hydrogen in a metal. And that allowed for the theoretical description of hydrogen in metals, which was carried out in the 1930s. Theoretically, the basic idea in a more modern language might work like this. In thermal equilibrium, the chemical potential in the gas phase matches the chemical potential in the solid phase. And you can make progress because for the gas phase, especially at low pressure, you have very accurate theoretical estimate of the chemical potential, which means that if you have the gas in equilibrium with the solid, then you know the chemical potential for the hydrogen in the solid and gives you a tool to study things. So in the gas phase, the chemical potential, there's sort of standard formulas that can be used. The F is fugacity, and fugacity requires some work and is important at high pressure. At low pressure, the fugacity is just the pressure. You can have various models for octahedral site occupation. In the 1930s, people did models based on octahedral site occupation. Neutron diffraction experiments in the late 50s and early 60s identified octahedral occupation in palladium deuteride. Well, I spent a lot of time in palladium hydride over the last few years trying to make up statistical mechanics models. I didn't do equivalent models for palladium deuteride. And in spite of all the work that our communities put in, the palladium deuteride phase diagram and isotherms are nowhere near as well studied. We don't have an equivalently good phase diagram in the literature for palladium deuteride. I'm interested in the problem because I'd like to be able to put together a simulation model for the Fleisch-Pons effect. And if I want to model, if I want to have a decent physics-based model for loading of deuterium into the palladium, I'm going to need to know the chemical potential. So all of this provides motivation for the present studies. So I want to begin by thinking about alpha phase models. If I look at the phase diagram, and this phase diagram would be the transient phase diagram. So Mike Staker the other day talked a little bit about the equilibrium phase diagram. And I'm in this presentation, I'm assuming that the atomic self-diffusion of palladium is sufficiently slow that we're not getting vacancies. So all of my palladium atoms are locked into FCC-type lattice for this discussion. But you can see at low loading there's an alpha phase, and high loading you can see a beta phase. The question is, what the heck is an alpha phase? Well, that hydrogen goes into octahedral sites sort of randomly. God rolls dice, and there you have it. In the alpha phase, at low loading, you have the possibility of making sort of a simple approximation from the formulas we had before by basically taking the O-site occupation to occur at a particular energy. So in this formula, the octahedral site energy is just E sub O. And you can make a relation. This relation was figured out in the 1930s. This relation was basically the very first model for loading of hydrogen in palladium. So if you plotted the pressure times this function of loading, 1 minus the loading quantity squared over the loading squared, in principle it should depend on temperature. In fact, on the right-hand side there's an exponential dependence. So if you made a log ln plot, it should be approximately go like 1 over t. So if you look at the data from Cluley et al. Back in 1973, which I'm of the opinion is an extremely important data set. It's data for palladium hydride in red and palladium deuteride in blue. At large values of 1000 K over T, which corresponds to low temperatures, you see straight lines forming. And at high values of pressure times 1 minus loading squared and so forth, the curves tend to roll over. So they're deviating from straight lines. And what this means is that the simple formula we got in the previous slide works pretty well at low temperature, but at high temperature, the simple model doesn't work very well. So question is how should we think about this? Did the experimentalists make a mistake? Well, no, these experimentalists certainly didn't make any mistake. The simplest interpretation is that there's more states available at high temperature than are present in the simple model, assuming octahedral sites. So one possibility is to expand the simple model to include tetrahedral site occupation. So if you think about the lattice, the FCC lattice, you can think of a checkerboard where maybe in one plane the palladium atoms are sitting on the black squares and the deuterium atoms are sitting on the red squares. If you go up 1 unit, you shift the checkerboard over, and if you go up 2 units, you shift the checkerboard over another. That gets you where the octahedral sites are. The tetrahedral sites are sort of stuck in the middle. And it's indicated here, and it's perhaps hard to see. Anyway, people have done density functional calculations like what were just described for these kinds of lattices. And the density functional calculations over the years have been improving because the codes have been improving, the approximations have been improving, and they've been more and more fine-tuned to be able to handle palladium hydrogen occupation better and better. So in this case, the tetrahedral site occupation energies are calculated to be anywhere between 50 and 150 millivolts above the octahedral site. So the O to T excitation energy, by theory, would be somewhere in the neighborhood of 50 to 150 millivolts, which is well enough, certainly low enough to lead to occupation at the elevated temperatures of the Cluley et al. Data. To include this into the model, we could calculate the chemical potential for hydrogen in octahedral sites and the chemical potential for hydrogen into tetrahedral sites, and then we can solve the balance. The result when you do this for this simple kind of model looks like this. You can fit the data extremely well, whereas without extra sites such as tetrahedral site occupation, you have trouble fitting the data at all, especially at high temperature. And what I found from this study was that the T site, tetrahedral site to octahedral site energy difference was about 100 millivolts, which is smack dab in the middle of the range of the most accurate density functional calculations. Originally, when I did this work, I was expecting a bigger energy difference, but this is what the optimization gave. And this is interesting. I'm actually surprised that people doing the density functional calculations haven't gone back to the data to try to figure out how well the codes are working relative to Mother Nature. For the phase diagram, since there exists good phase diagram in the literature, and since we have a statistical mechanics model with octahedral site and tetrahedral site occupation, which works pretty well in the alpha phase. The question is what can we do for the phase diagram more generally? Now, there's lots of issues associated with this. A gigantic issue is if you believe that there's tetrahedral sites, and if you believe that in the alpha phase at low loading you happen to know the excitation energy, well, that doesn't mean you know what the loading is at other concentrations. And the basic issue is as you add more hydrogen, your lattice expands, and as your lattice expands, the energies of the states are going to move around a little bit. So we need some way to get some idea of what the tetrahedral site energy might be. And there's an Australian group that did some neutron diffraction experiments, which I presume that Ed Storms was referring to briefly earlier this morning. And there's some weak evidence for emission that would correspond to the space group that would match tetrahedral occupation. And it's possible to interpret the strength of those lines in terms of a statistical model from which you can calculate the tetrahedral site energies. And I've done that. The green triangles are the inferred excitation energy based on the neutron diffraction scattering. The red circle at low loading is the result of the optimization against the alpha phase data of Cluley et al. And I also worked with these models at very high loading to see if I could connect with the small amount of very high pressure measurements that have been done. And if I relied on the old high pressure measurements by Baranowski and all of hydrogen in palladium, and also try to work with some of the very high pressure experiments of deuterium and palladium, also by Baranowski and so forth, then the only way to find any consistency at all between the experimental data and also between the resistance ratio curves is to pick O site to T site excitation energy near 225 millivolts. If you go much higher, much lower, the predicted model curves don't have a whole lot to do with experimental observations. So given this, we're in business. However, the notion of octahedral site occupation is extremely controversial in the field, and especially near unit occupancy. So one thing that we're going to need in order to keep the various folks involved from strangling each other at conferences in front of an audience. So we're going to need some experiments that can settle the controversy. Okay, so in the case of palladium hydride, I went ahead and there's this neat online app that allows you to digitize data from published curves. So I took the published phase diagram. I digitized it. I used the alpha phase model to extrapolate to low loading, which I think actually works extremely well. I've compared it to quite a few experimental data sets, and it agrees. I tried extrapolations at high loading and into the high temperature, high pressure region to make some data points there. And I fit it with respect to the model. And I get an O-site energy curve that looks like this. One comment about this is energy, not enthalpy. And another comment is that occurred to me while Ed Storms was talking about the enthalpy, that my energy actually is shifted off by 3/2 times the 0 point energy. And I'm going to try to go back and think about what that means in terms of trying to connect to the enthalpy and so forth. But what we see is when I got this, I was actually very surprised by it. At low loading, there's some splitting, and I had been expecting some splitting due to the electronic density of states and the energy shift you get when the electrons occupy the different electronic states. And that seems to have come out from the optimization for the phase diagram. There's some discussion in the literature of this, and my estimates from this actually match rather well to the estimates people have made from the density of states in the literature. At high loading, the curves go down, they come back up. I get some splitting at the different temperatures. And the splitting I attribute to occupation of the different, or I attributed to occupation of different configurations. There's more to be said about this, which we'll come back to before too long. There's some question about whether the empirical extrapolations at high temperature, high pressure regime are accurate. So there's no equivalent critical review for the palladium deuteride isotherms. The published isotherm data is inconsistent. So let me take a selected set of these isotherms and plot them. There they are. Some isotherms taken at the same temperature are at different places by a lot. Some isotherms at different loading simply cross. Some aren't straight, and the miscibility gap. Anyway, it's a three-ring circus for the data. So in order to try to make sense out of the phase diagram, I'm sort of a fan of a small number of groups and authors. I think very highly of Lasser. I like Wiki, and the data of the group of Sakamoto and company seem to make a lot of sense in connection. So you know you've got problems when you've got a theorist selecting which isotherms from experimental groups to use for a phase diagram. And I'm kind of hoping that Ed Storms or other experimentalists might chime in and get us some reliable isotherms to work. But the isotherms I chose look like this, and I've extended these again using the reliable, what I believe to be reliable alpha phase model to get low loading tails here. But otherwise, we've got data sets that go up to about 100 atmospheres here. Okay, so we can fit them, and we can use the model to fit them. And there's lots of issues associated with this. These data sets aren't quite as self-consistent as for the palladium hydride, so the fit isn't quite as good as what I got before. All is said and done, this looks halfway decent to me. Because of the various constraints, I added, for this particular fit, I added a point at high loading, which is in line with experimental observations near room temperature. At elevated temperature, I pretty much arbitrarily added a point in order to get the curves of the energy and the general fit to be physically sane. And here's the O-side energy curves that I get for this particular model. And this is a little bit different from what I had before. I didn't have the freedom in this fit to get the splitting at low loading that I'm expecting that was present in the palladium hydrogen. Plus, the data is not really good enough to give it to me. At higher loading, I actually think this curve is probably better than the one I got for palladium hydride. And I've been putting in work to make an equivalent curve for the palladium hydride phase diagram. Bottom line is this seems to work okay, and we now have a statistical mechanics model that we can use for palladium deuteride, sort of on similar footing for palladium hydride. In the beta phase, I had done some work trying to make isotherms that extended off to high loading. So in this case, this particular model sort of sails through a loading of 1.0 with no discontinuity. My friend Ed Storms, he doesn't like that at all. If you go through 1.0, there's got to be a discontinuity of some sort. We would all like to see a discontinuity. I would have liked to see a discontinuity. And what I found is that for such a relatively low octahedral site to tetrahedral site excitation energy, there's not much of a discontinuity. The discontinuity is much more subtle. If the T-site occupation energy were over 500 millivolts, then in that kind of model you can see a pretty sharp discontinuity. But in this kind of model, there's a much gentler thing. You can see a version of it for the O site and T site occupation. The tetrahedral site occupation in this model shows sort of a gentle ramp up near a loading of 1.0. And again, at the moment, since we know so little about from experiment about T site occupation at high loading, this is just a model, and we're going to need experiment to sort it out. Anyway, the conclusions is I think these models are interesting. I think T site occupation, especially at low loading, is predicted. It's consistent with the best DFT calculations. There's experimental data, weak experimental data, but some experimental data from the neutron diffraction to support it. Much more can be done to remove uncertainty, and should be done to remove uncertainty. Anyway, I'll stop here. Thank you.
Minutes to discuss. Okay.
Well, Peter, I sympathize with your efforts to find good data in the system. We all want that, and if you can massage it properly and make it look good, that's even better. But one of the things that I would like to point out is that when palladium deuteride is loaded and deloaded, irreversible changes take place. Now, people who have made many of these measurements ignored that. And they would load and deload because that process activates the material, makes it more readily reactable, and therefore it's good for their particular study, without recognizing that they were changing the nature of the sample. So we have got to recognize that each time palladium is loaded and deloaded, you're working with different material. The effects are irreversible, and they are important. And my data showed just how important they are, even with respect to the thermodynamic properties. And certainly the mechanical properties and the shape and size and volume are very apparent. So we're not working with the same material. So we have to start working with the same material. Thank you anyway for your efforts.
Thank you for your comment. You're preaching to the choir here.
Just curious, what is the difference between PdH and PdD that they don't overlap? Is it a function of the bosonic nature of deuterons, or is it the mass difference?
That they don't overlap? How do you mean?
They're different. The phase diagrams are different.
Right. Certainly there's some 0-point contributions, which gives you an offset, and that's responsible for most of the difference between the phase diagrams. Basically, when I started this, I said, well, why don't you just take the palladium hydride phase diagram and just shift it by a constant in honor of the 0-point energy? And I did that as a first approximation. It gave me a very nice palladium deuteride phase diagram. So
it's
yeah,
that simple then?
Pretty much.
Yeah, just to reinforce what Ed said and Peter agreed with, you either by gas loading or electrochemical loading, you can't get to high loading without backing off at least some. So the cold work is inevitable. In order to restructure the surface to allow high loading, you have to cold work the material. So it simply changes every time you do it. In terms of, this thing is nice. I never expected any discontinuity at a loading of 1, and certainly never observed any discontinuities at loading 1. The thing just seems to sail through 1 nicely. Some of Baranowski's data, though, there's a second-order discontinuity. There's a change in slope at that point. Do you have any thoughts on that?
I use that change in slope as one of my several independent ways of estimating the O-site to T-site excitation energy at high loading. And it gives me the same number as I get from the other ones. So I do believe that slope change is consistent with the basically going above a loading of unity. I will point out on this curve that that the region near loading of 1 is easily accessible. All you need is like 1 to 3 gigapascal here. So,
Just small question.
Okay. I would just like to make one comment about the discontinuity at 1. That is characteristic of the formation of another phase. There's no reason to think that the beta phase center cubic beta phase, continues beyond 1. You would expect a discontinuity when a second phase formed that has a higher composition and a different crystal structure. That kind of behavior is typical of all compounds when they change, when you form another phase. And so I would expect you don't want to try to extrapolate your theory beyond that because you're extrapolating it into a 2-phase region.
We desperately need experimental results here that clarify this point.
Okay, thank you.